Okay, we have learned the very basic structure and also very basic reaction of alkene so far. And now we are moving into real reactions. So we are going to learn all of this. It looks like a little scary, but actually, if you go step by step, it's not too much we can do. So we have learned this one. Okay. So with alkene has electron rich, high electrons, electron donating. Okay. So we call them nucleophile. And reaction mechanism for them, as you have seen, first step is that this electron is donated to proton. Catch it. What is the intermediate? What is the intermediate? Carbocation intermediate. What is the structure? Planar structure, right? So and then here the HCl minus or the Br minus will come back and attack this position, alcohol group. A little variation, you can add halide and acid separately. So anyway, acid can protonate and forming carbocation, and then I minus come back and attack this position, not this position. There's a little modification. Further modification, if there is good nucleophile, many nucleophiles, so I minus water, both of them are kind of weak nucleophile, but if there are a lot of the water, okay, acid protonate, and then water attack this position. So this is all we have learned so far. Okay? So alkene, electron rich, is ready to donate electrons, pi electron. Now if it meets the first reaction we learned, halogenation. Instead of HX, if it meets X2, okay, what do you expect? Die. The product is like this. And if you look at that product, maybe you can think the possible mechanism, something like this. CSL or BRBR, so originally there was equivalent. If it's breaking in the middle, that's a dissociation energy required. For product is radical, right? Prolific cleavage. But in this case, if this two electron is donated here, and then this electron is moved here, that's a heterolytically cleaved. If that happens, then maybe Br is added here, and then positive charge happens here, and Br minus will come back and finish up the reaction. Seems like it's very similar to HBr addition. Is this the right mechanism? Is the question. First of all, HBr case, originally HBr, it was not fair bonding. Which side is a reddish?
Yeah.
Which side is more electron rich?
Yeah.
Originally it was like this, right? That's why attack position was clear. Alkene has extra electron rich, that donated that electron to this position. So cleavage also, so naturally it's breaking like this. H plus Br minus makes sense. But in this case, there was a Br, it was equivalent. Why one Br becomes Br plus, the other becomes a Br minus? It's a little strange, right? And if you form this kind of intermediate, if it's a carbocation, planar structure, if that Br comes back, then what do you expect? The attack position is up and down, should be equivalent, half and half. So to check that mechanism, so this kind of a reaction, ring structure, and then Br is added, and this product is formed. But this product is not formed. Only this is a formed, not this one. Then can we think the intermediate is really carbocation? If it is a simple carbocation, like a protonation, then the product should be attack, up attack, down attack should be half and half. It should be mixture. What is the relationship between these two? Yeah, you know? Enantiomer. Is this mirror image to each other? Is that mirror image? No, then it's not enantiomer. What is the relationship with it between? Stereoisomer, okay, it's a better isomer. Yes, it's isomer. Among the stereoisomer, yes, correct. What is the opposite word of a stereoisomer? Isomer. One side is the stereoisomer. What is the other side of isomer? Structural isomer. Okay, at least that is the stereoisomer. Among stereoisomer, what is the relationship? Diastereomer. This is diastereomer. Diastereomer has two kinds, right? Cis-trans diastereomer or positional. Actually, this is both. RS you can give. If this is RS, maybe it's RR or something like that. Okay? So that's a diastereomer. Now, the question here is, why only this is formed, not this? That's the question. How can you explain? If it is a simple carbocation intermediate, you should have 50-50 of these two products, but this is not formed. And this is formed. Only this is formed. So, one explanation was, when electron was donated, this Br does not go to only one position. It's in the middle of these two carbon. They're forming this kind of cyclic intermediate was suggested. And this Br plus, Br minus, Br2 we call bromine. Br minus, what do we call? Bromide. And Br plus we call bromonium. Ium is a positive charge, hydronium. Okay? And hydrogen, hydride. Same way, ide is an anion. Br minus is the bromide, and it's a bromonium intermediate is suggested. Why? If this is formed, this is a kind of fixed structure, not free carbocation. If this is intermediate, then possibility is, if this is formed, then the attack position of a Br minus, it can happen only from behind and push this direction. So direction of the electron movement from top going down and push and then further go down. It's on the same direction. And if it comes from here, then electron comes up, attack, and it should turn. You turn, right? That's not very smooth flow. So smooth flow is going in, push, and then further go down. This is the smooth direction. Okay? So that's why the attack does not happen through here, and it does not form this product. Intermediate is formed somewhere here, and then the other one attack from the top. If intermediate is formed from the top, then Br minus attack happens from the bottom, and it may form this and then the other form here and here. Maybe enantiomer can be formed, but that's also trans. So only transform is produced, and then this kind of intermediate was suggested, not proved. Okay. If it forms this kind of rigid intermediate, then attack can happen only one direction here, and then it can form trans product. Sometime later, actually many years later, this was proved by George Orloff, the organic chemist in US. And all of those cases, he could not isolate this intermediate because if there's any reasonable nucleophile, anyway, they finish the reactions. You can see the product, you don't see the intermediate. So he thought if he removes any kind of good nucleophile, and to do that, he used this kind of intermediate. Usually, this one is not good Levy group, but by giving strong acid, there is no good nucleophile. No nucleophile, then unstable intermediate could be isolated. So by this method, this attack here, and then push this out, it forms this bromonium intermediate, and there is no reactive partner. That's why that could be isolated, even crystallized, to give really that structure is this kind of triangular intermediate was formed. Okay, so we learn one more reaction here. Let's compare with the HBr and Br2. This is slightly changing reaction. First reaction, high electron attack the proton, carbocation form. Okay? So there is a selectivity for the better, more stable carbocation we have seen. That's Markov-Nikov rule. And then BRBR. And affect this one first, and then intermediate is formed. This is kind of a stable intermediate. That's why Br plus can be taken by pi electron, and Br minus is released. And that Br minus comes back and attack here and finish up the reactions. Okay, similar. Now, next reaction. Very similar, but in this case, now X2, the first intermediate would be halonium intermediate. And then now if you add water, we have seen similar case before, HX reaction, if you add water, now they compete. Water is a nucleophile, X minus is a nucleophile. Okay? Then intermediate is same bromonium intermediate is formed, and then they compete with X minus and water. And if water amount is higher, then water can attack here and ring open and form this product. Okay. Now in this case, this is a halo, this is a hydro. So together we call this kind of product as halohydrin. Name is not important. The product structure is important. Okay. It's very similar to the examples we have seen. HX with water. Okay. So in this case, 8X2, chlorine or bromine, they are used as activating group, activating the pi electrons. Double bond nucleophile, electron rich. To activate it, we can add acid H plus to make a carbocation, or X2 added there, and then forming intermediate, aluminum intermediate, and then it is attacked by nucleophile. By the way, Cl2 is a human-friendly reagent. Have you heard Cl2 being used in World War I as gas? What do you call the gas name?
Mustard gas.
Is that mustard is a little different one? Cl2 anyway, Cl2 is very toxic to human. Br2, what do you think? It's also very toxic, especially it is known to be more toxic to male, making you sterile. Sterile means clean, means you cannot make a baby. Okay? So Cl2, Br2, those reagents are very toxic to the human. Okay? That's why to replace those reagents, this kind of reagent has been developed. So-called N-bromosuccinimide. Now in your level, maybe structure mechanism is not very important. At least the name of NBS. NBS is a slow generator of a Br2 in the middle. It provides Br2 slowly to the reaction, and you add the water together, then you can expect pi electron is activated by polonium, bromonium. Okay, bromonium is formed, and then add the water, and water attack this position. Anything strange here? Why water does not attack this position? Why water attacks only this position? When we said those selectivity of Markovnikov, we said carbocation stability. Okay. Tertiary carbocation is more stable than secondary, than primary, than method. Now, if you assume this kind of a cyclic intermediate, the bromonium, then why water does not attack here? It attacks only here. Isn't it strange? Explanation is even though it forms this kind of bromonium, it still prefers a little shifted. This position is a little more positive than this position. Still, it has a partial carbocation character. It's not symmetrically triangle. It's a little remote here. That means this is a little more electropositive, and attack position of water is still this position is preferred. Okay. Product is trans product is formed, but selectivity of a position is still similar way of a Markovnikov way. That's the explanations. So that's in between of this triangular structure versus this the intermediate. May not be equilibrium. This is like the resonance structure. Okay. Not fully this open form. It's still closed, but this position is more positive to the attack. Okay. Question?
Why PR shift to like
Originally we expected this is intermediate, right? Because this one is a secondary carbocation, this is a primary carbocation. But we found by the cis trans product, it may have this kind of the ring structure as intermediate. But for product, selectivity is always attack this position. So this is more like this character. That's why this intermediate may be in between. So this is perfect symmetric triangular, then OH should attack here or here equivalently. But reality is maybe this is in between this and this. A little shifted, a little more character of this. Okay. So this is the bromination, the halohydrin reaction. By adding X2 and then add the water, and the product is a halohydride. Okay, now this. Now here, a little simplified version but similar. Pr2 is added to activate. And bromonium forms here. Now water attack either this position or this position. And major product is which attack this position. This is following Markovnikov or anti-Markovnikov. If you look at the product, two position and then two added. So this is the addition reaction, right? Now when we decide Markov, the Markov is the second addition one, this is the activating group, added here. And then water attack this position. Okay, so this is Markovnikov product. 하나밖에 안 배웠어. Originally we learned HX, now X2. and we added water. Okay. Okay, move on. Hydration. What is the meaning of hydration? What is the meaning of hydration? Add water. Okay, that's hydration. 물칠하기. Add water is hydration. Okay. If you run and we sweat a lot, then we are dehydrated. 탈수. Then we add back water. That's hydration. Okay. Then to double bond, if you add water, what's the product? Water is added to the double bond. HOH. That's hydration. Okay. Have you learned before? Acid plus water, that was hydration. Okay. Double bond, you add acid and protonate, forming carbocation, and add water. Then product was HOH. So that reaction with a double bond with acid and water, then product is hydration water. What's the temperature? 250. And strong acid catalyst. Phosphoric acid, sulfuric acid. It's a very strong acid. Strong acid, high temperature. It's an industrial scale to make ethanol. But in the laboratory, it's difficult to heat up to more than higher than 200 degrees. So this is industrially, you can understand by adding acid and water that we can give proton and hydroxyl group. That's hydration. But we need to have a little smoother reactions. Mechanism by adding proton, activate, and water attach to the carbocation. That's the mechanism. For ammonium case, we assume there is triangular intermediate, cyclic intermediate. Protonation, we don't have it. Proton is very small, just add it, just to form more stable carbocation. Secondary, tertiary carbocation, and water attack their conditions. Markov-Nikodym product. So to make this hydration a little smoother, which you can do in the laboratory, activation group is to change it with a different reagent, not proton. Hg acetate, mercury acetate, acetate -1, and Hg is a +2. Metal +2 is an acid, base, oxidant, reductant. It's a reductant. If it's a metal itself, it's a reductant. It gives electron and it becomes cation. If a metal becomes stable cation, is that acid, base, oxidant, reductant? That's acid. That's electron poor that attract electrons. Okay, that's acid. Acid is electrophile. Okay. So by adding metal cation, then that is added to this position, similar to proton. Okay. Previously, we have seen adding proton to activate this double bond, forming carbocation, right? But that requires very high temperature. We don't want it in the laboratory. Now, definitely organic chemists, they tried the different acid, weak acid, and mercury was found that if you add the mercury, then mercury is added. And then later you treat with foreign reagent. This is a reducing reagent, and reductively cleave off. Then it generates this product. And let's look at the mechanism. Mechanism. First step. Mercury is added, similar to proton. So this is like cyclic, similar to bromonium, kind of cyclic but intermediate. And then water attack. Which position? More substrate position, which is similar to this case. Okay. Bromonium also, more substrate position was preferred by water attack. Similar. Okay, it's a more stabilized carbocation character it has. Even though it's a cyclic form, more positive characters here. Same way, mercury is added and water attack happens here. That means this triangle may be a little shifted this way. Okay? Water is attacked here. And this is another intermediate. Now you need to remove this mercury. That removing of that metal, you can do either oxidatively or reductively. In this case, boron reagent is H minus. Electronegativity wise, what is electronegativity of carbon? 2.5. Hydrogen? 2.1 or 2.2. Boron? Boron is like metal, weak metal. Okay? If you have a BH3, H character is H minus or H plus? It's H minus. So it is similar to 3 hydride attached here. Make this into BH4. This adding one more here, and then this is a plus charge, minus charges, and sodium. This is a salt form of BH3. Both reagents, BH3 or BH4 minus, they are hydride source, H minus source. H plus was acid. H minus is ready to give electrons permanently. That's a reductant. Okay. So that's why BH3 or BH4 minus, those reagents are reducing agent. So if you add that boron reagent, they cleave this mercury position by giving that electron to here. That's why it's treated as without leaving any trace and flip off. Now product wise, reaction product wise, you started with double bond. And product is H and OH. Hydration.
Yes.
Reaction itself is similar to acid condition, water adding reaction. Now product position is that Markov-Nikov or anti-Markov-Nikov? It's a Markov-Nikov. OH was added to more substitute positions here.
Yes.
Okay. So this is modified mild version of hydration instead of acid catalysis. Okay. Now, sometimes we need to add that water not on the hydroxy group, not on the more substitute position. Sometimes you want to add that this position. Then this is option. Now let's compare. In this case, we use BH3, this reagent we use, to the double bond. Then this forms 1H is added, and then B is added. In this case, B is a plus charges, and then H is a negative charges. It is added like this. And then now we need to cleave off this. For cleavage, in mercury case I said, using reducing agent, reductively cleave. Now in this case, we can use hydrogen peroxide. This is an oxidant. Oxidatively cleave. Then this oxygen is inserted here. And then this B is removed. And this is the product. Before we look at the mechanism, by looking at those in the product, is this a Markov-Nikov product or anti-Markov-Nikov product? This is anti-Markov-Nikov. We have two options. If you want, in the laboratory, if you want Markov-Nikov, we use mercury and then reductively cleave. When we add the mercury, hydroxyl is also added. And then we remove mercury. The other method, we add boron reagent. and then we remove boron, and when we remove it, we oxidatively cleave, and hydroxyl is added in that position. Okay. A little complicated, but this is the most complicated part. If you overcome this, then you can go downhill. So first reaction we call oxymercuration. Oxygen and mercury is added together, oxymercuration. Second reaction we call hydroboration. Hydrogen and boron was added first, and cleavage was done oxidatively. We'll see several examples further. Now, boron reagents, as we said, boron is a more electropositive than hydrogen. That's why hydrogen has a H- character. Boron is very electron poor. It's like magnet. That's why itself is quite unstable. That's why usually we use that as ether complex. THF tetrahydro the furan. This is a usual solvent to store and then for the reaction of a boron reagent. If you add this, then this is electron around the boron is how many electrons there?
0.
How many electrons? Hydrogen, helium, lithium, beryllium, boron has 3 electrons, right? And then 3 electrons is matched with each hydrogen. So totally this is a 6 electron. It doesn't satisfy octet rule. It's better to have 8 electrons. That's why if to make complex, this electron is donated to this, and it forms like this, then now both of them are satisfying octet rule. Now this one 1, 2, 3, 4 bond. This one 1, 2, 3, and the local electron. Both of them are satisfying octet rule. In this case, this plus minus is that oxidation number or formal charge. That's a formal charge. Okay, it's not oxidation number. That means oxidation number is not changing. That reaction is not oxidation reduction reaction. That is similar to acid-base reaction. And donate electron, but temporarily. That means when they leave, they remove that electron. Okay? So this is kind of intermediate, temporary complex fluid reactions. Now by adding this, BH3 can be added one time, then BH2H can be added. Right? But this BH2 that still can donate H and B, and it can react with another one, and then another one can be added here, and still there is a BH. It can be added to still another one. One BH3 has 3 hydride. That's why it can react with the 3 double bond. So this is intermediate. Then each intermediate, now if you add oxidizing reagent, then insert oxygen here, here, here. Then product is hydroxyl cyclohexane. Now if you compare this one and this one, OH was added here, proton is added here. Okay. So this is a hydration reaction. And the message here is 1 BH3 has 3 hydride. It can hydrate 3 molecules of the double bond. Now let's look at this. Now here, if you have the BH3, then one position BH2 can be added, and then proton can be added. And then the oxidation can cleave here and generate OH. Now let's think. What generates this kind of an intermediate, not the other one? BH3 can be here, and H can be here. Right? Mercury case, stability of carbocation character was more important, similar to bromonium. Okay. More substrate position has positive character. That's why that position was added by water. Hydrogen case, the boron case, hydroboration case. Now, there is no carbocation character here yet, and no other the charge separations here. In this case, more important thing is steric hindrance difference between boron reagent and hydrogen. Hydrogen is much smaller than BH2. That's why this goes into a more steric position. This goes into a more open position. That's why BH2 is added to more open positions. Secondary position and this tertiary position. And then oxygen was added by removing this boron. That's why oxygen was added here. That's one thing to say. The other one, if you look at those stereochemistry, when we looked at the bromonium case, attack of a nucleophile happened behind, right?
Yes.
That's why the product was trans product. Hydroboration case, the product is cis product. When this BH2 and H was added, it is added from the same directions. BH2 and H was added at the same time from the same direction. And direction, this one is more bulky. That's why not this direction, it is added this way because this is bigger than proton. That's why it is added to less bulky positions, added the same direction. And when the workup was done, hydrogen peroxide attacked from behind here to the boron positions. And then add oxygen in here. That's why this carbon position was not touched. Originally, BH2 and H was added to the same direction, and then that BH was replaced by oxygen. That's why in the product is cis product. It's a big difference, right? Mercury case, we didn't have to look at it, but mercury case is similar to bromonium. Mercury is added first, and then hydroxy is attacked from behind. But mercury case, anyway, this position will be reduced. That's why it leaves only hydrogen. That's why we don't see the effect. But anyway, the attack is, if it's a cyclic intermediate, the attack should happen from the behind. But in this case, if it's added together from the same direction, it's added. Okay? Then boron can be replaced by oxygen from this side. So that's why this was not touched. Cis product we get. So this is a summary. Now we have this kind of a double bond. We can get two products. Either oxygen is added here or oxygen is added here. So one proton, one hydrogen, one OH, hydration. Water is added. Two options that we have. One is oxymercuration. The other one is hydroboration. That's only the same first step. Okay. Oxymercuration case. Adding this, forming mercury intermediate. Water attack this position first because this is a carbocation, more similar to carbocation position. And open up. And mercury is here. Then mercury is reduced by this boron reagent and removed. And the result is oxygen, hydroxy is added this position. Hydroboration. BH2 is added this position. Hydrogen is attached to this position because this is more bulky positions. And B is replaced by oxygen. Okay, if you think about when the oxygen was added, then you can get the answer. Which position is oxygen is introduced? More substitute Markovnikov or anti-Markovnikov. Okay. Hydroboration, anti-Markovnikov. Oxymercuration, that's Markovnikov. Okay. Now let's think about this. If you want to make this product, what kind of starting material would you like to use? All reaction we learned is from alkene, we added the water, right? Hydration.
Yes.
So alkene precursor or alkene starting material, which alkane would you choose? You have two options maybe. OH here, then maybe double bond here, or double bond here.
Yes.
So let's say left and right. Which one to get single product, not mixture? Which one would you like to choose? Left. What is the problem for the right? If it's the starting material is here, what is the problem?
Same.
It's the same. This side is also secondary. This side is also secondary. So it's difficult to get the selectivity. Right? Now, if it's a left, so double bond is here. Okay. Now you want to get that product. Which condition do you need to use? We learned the two things. Yeah, you need to use a hydroboration because that product is anti-Markov-Nikolov product. Okay. So if you chose your starting material here, then you cannot get selectivity. You will get a mixture. OH here, OH here eventually. Okay. Now if you choose double bond here, if you have this one, then you will have this one mixture. That's why this is not a good choice. Now, if your starting material is this one, now you have options, hydroxyl added here or hydroxyl added here. To add here, that's Markov-Nikolov product, you need to use oxymetallation. If you want to add here, that's hydroboration and oxidative cleavage. 이게 제일 복잡한 거야. 여기까지만 하면 다 왔어. Okay. After here, you also need to know start with the mercury or boron. That's what you need to know. And also you need to know how you finish up the reactions. Reductively or oxidatively. Okay. Only oxidatively at the cleave you can add oxygen. Reductively you just leave only hydrogen. Okay. A little complicated, but this is all. Okay. Now, with this, that's why this is the reaction example. BH2 is added here, let's say into the position, H is added, and then oxidatively replace this with oxygen. Okay, let's do a little more. So far we have learned, until last week, we have learned the HX reactions. Activated with the proton. And then X minus attack. Carbocation stability was the issue. Or we can add water. Okay. Now today we learned X2. Bromonium intermediate. And then nucleophile attack behind. Then product is BRBL or halohydrin. Water can be attacked here too. Okay, bromo and hydroxyl. Okay. Now, the next reaction we learned is hydration. Hydration, conceptually, that's acid and water, but that reaction is too vigorous. 250 degree and very strong acid. We don't want it in the laboratory. That's why a little mild condition, we chose two reactions like this. Okay. Double bond there, we choose intermediate, two different intermediate. Mercury intermediate or boron intermediate. Okay. Mercury intermediate, when the mercury is formed, water attack right away on the more substituted position. Boron attack case, boron is added more static position. In this case, not electric issues, this is more static issues. H was added to more open position. Okay. And then boron was replaced by hydroxyl. Okay, that's what we have learned so far. Okay, best way you arrange your reaction of the examples, try to connect everything step by step. Then, even though you learn a lot more reactions, still you can arrange and you can classify, okay, that was done by that mechanism step by step. Okay? 그래야 숲속에서 길을 잃지 않아. Okay? So now let's think about reduction. In this case, reduction means hydrogenation. Hydration is adding water. Okay? Hydrogenation is adding hydrogen. Okay? That's a difference. Hydrogenation. Hydrogenation, now we add X2. This looks like the product, it looks like similar to X2. H2, X2 looks like the product is the same. Mechanism is not same. X2 case, when X is clipped here, okay, brom is clipped, it forms bromonium intermediate because this can form this kind of a stabilized intermediate, and then Br minus is formed. If this goes to that mechanism, the first one is proton can be captured, and then the other one should be H minus, right? H minus come back and attack. Maybe you can draw that mechanism, but you should remember that H minus is very unstable. In a sense, H minus is very reactive. Br minus is quite stable. Okay? Usually, H source we see in aqueous media, the H plus. H plus is much more common and more stable. H minus is very exceptional. That's why if this attacks this pi electron rich, if that attacks here, similar way to this, then first step may be okay, proton can be captured, catalytically cleaved, but H minus generation is not favored. Similar situation we have seen in radical reactions. Radical reaction, H dot generation is not favored because H dot is not stable. Okay. IQ radical was more stable than H dot. We have seen that cases. Same way, H minus is not stable. That's why that mechanism up. In this case, the reaction is more similar to borane addition. So in this case, by adding metal catalyst, either palladium or platinum is more expensive than palladium. I say this because platinum is more reactive too. The more expensive one is more reactive. Okay. Using metal itself or the metal oxide anyway, palladium, platinum, nickel kind of hetero, the transition metal catalyst, and then add hydrogen gas. Okay. H borane reagent case, we have seen H and borane was added together, right? It was not fully cleaved, it's added together and then bond was cleaved in between. Similar way, when we add H was added, now as you see here, they are added as cis addition. Implies that the two proton was added together, two hydrogens are added together from the same side. That is more like this. H2 is equivalent. It's difficult to form. H plus is easy to form. H minus is difficult, I said. That's why usually it does not dissociate H plus, H minus. And this is metal surface. It goes attached to the metal surface. And then by making new bond to the metal surface, this bond, the HH bond is becoming weaker. So it's almost like the H radical. H. Not fully, but it's kind of a tend to leave. Here, the double bond comes in and then attach, comes in, and to this hydrogen, there comes in and then capture both of them. So and the result is 2H is added to double bond together. Okay? It's a little extreme the case. Looks like it's two hydrogen is fully detached, but it's a little too much to describe it. It's a little weakened by activated by metal surface. And then double bond comes in and then capture both of them. That's why hydrogens are added from the same side. Makes sense. So this is almost working together, concerted manner. Concerted means that they worked together. So through this mechanism, now H2 can be added. Same side, either from the top or from the bottom. Now, if choices, in this case, bottom up, it generates two different products. If it's up, then you may form this product. if it's from the bottom, this product. In this case, this is dominated by this, explained by this another static hindrance. It's a more static hindrance here. That's why it's difficult with H2 ADD here. It's an open form, that's why H2 is very small, you may think, but you should remember that this H2 is on metal surface. So metal has static hindrance, and then double bond should come here. Okay, this side approach here, it may have a static problem with the metal surface. That's why it's difficult to approach this direction. It's easier to approach a metal surface through here. Okay, makes sense, right? That's why less static on the side, or in other words, more open side is approached by hydrogen and hydrogen added here. So this is hydrogenation. As an end result, this is the reduction. Is that really reduction? Can you calculate? Now here, this one and this one. This position of the carbon. What is the oxidation number of this? This carbon, oxidation number? Zero. This carbon is a mid carbon, carbon, carbon. Zero. How about this? It's -1. Carbon, 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 and this is the H. Carbon is more electronegative. From 0 to -1, reduced. In oxidation number calculation, we assume that the bond is covalent bond or ionic bond. 100% ionic bond, we assume. Okay, that's the definition of oxidation number. Okay. Electron is more shifted to carbon direction. That's why it's reduced. Okay. So the title was a little bigger, a little big, reduction of alkene, but we just learned only one thing, hydrogenation. Okay. So by adding hydrogen, we need to activate hydrogen by metal surface. Okay. And then two hydrogen is attached together to the same side. Which side? More open side. Less electric, less static hindrance side. Okay? Okay, let's look at the examples. Now, this solution is in a sense, on the surface, two hydrogen atom is attached. This is kind of equivalent. So that's why this position of addition is more preferred to equivalent side. Means more same carbon-carbon double bond rather than carbon-oxygen double bond. Carbon-oxygen side, electron is not evenly distributed. More electron here, less electron here. Okay. Next semester we are going to learn reaction of this carbonyl. Carbonyl side, this is electronegative, this is electropositive. That means any nucleophile may prefer to attack this position, not this position. Okay. So that is a little polar bond. In comparison, carbon-carbon bond is non-polar bond, less polar bond. It's almost equivalent. That's why less polar bond prefers less polar region. Two hydrogen attached together, that prefers similar character side here, not here. Makes sense, right? So if you have a double bond, carbon-carbon double bond, and carbon-oxygen double bond, hydrogenation happens here. Even with low reactive catalyst. Palladium, platinum, I said, and palladium/C. Anybody knows the meaning of that? Palladium/C. What is the C? Carbon. And what does that mean? On carbon. Why on carbon? What kind of carbon? Why carbon? If you have a dirty air in the room, then usually we have carbon, charcoal, the room.
Yes.
Why?
아,
Ah.
가공성 구조 때문에.
In English,
폴리 폴.
if you make the charcoal, okay, then usually we remove all the materials from the inside, so it forms highly porous structure, many pores inside. With a lot of pore, it has more increased surface area. So palladium on carbon means mixed together with the palladium on charcoal, they are distributed on the small pores on the carbon. That means they generate more surface area to make a more reaction site. Okay? That's metal dispersed on charcoal. Okay? That's PDC meaning. Okay, so with the PDC and the hydrogen is added here. Now many double bond here, but benzene is very stable. Benzene double bond usually not attacked. Okay, this double bond is also polar double bond. If you add the hydrogen, it reduces in this position. CO is the polar. CN is also polar. Okay, CN triple bond is also polar. Now there is an option then only this one is reduced. This one is not same as the benzene, right? This is open, this is the cyclohexane, and double bond here. So hydrogen goes here. Okay, so if there is a multiple the double bond, like fatty acid, usually the 식용유, vegetable oil, we have this glycerol, trialcohol is attached to long chain fatty acid. So this is the vegetable oil structure. And those kind of oils, if you accumulate here and peak, then it's more solid. So those solid, basically the same structure like this, but they don't have this kind of unsaturation. They are all fully saturated form, and this is more rigid, and they form solid structure. If they have a more double bond, they are more flexible, and then they form liquid structures. So sometimes this liquid structure is solid form, and sometimes we wanted to make this into a little more solid form by giving hydrogenation reactions, and then you form this kind of a product. It has some name of those solidified vegetable oil, butter-like product. What's the name of it? Margarine. Margarine is the hydrogenated vegetable oils. It's a solidified vegetable oils. Sometimes it tastes quite good, right? And problem is, during those hydrogenations, if it's fully hydrogenated, it should be attached and saturate everything. But sometimes there is some isomerization happens, not hydrogenation. And majority of our vegetable oils, they have a cis bond like this. But some of them can be isomerized to form trans form. Then our nature, our body, we don't have enzymes to digest this. And this can be potentially problematic to our body, so-called trans fat. Trans fat is usually happened during this measuring production by hydrogenation. If everything is fully hydrated, no problem. Cis and trans, both of them will generate the same product, right? Hydrogen is fully added, then no problem. Partially hydrogenated, and then some of them is isomerized. This metal surface is intended to activate hydrogen molecule, but it can also activate this double bond, and it can change those directions. So industrially, that kind of heating or hydrogenation conditions, time to time can form small amount of trans fat, and is considered to be bad material for our body. Okay. I think maybe today, on Thursday, we are going to continue to oxidations. So up to today, we learned up to reduction, only one reaction, hydrogenation. Okay. Oxidation different way we can define, but in principle, adding oxygen. But adding one oxygen or two oxygen, okay, kind of different reactions we are going to learn. Okay, any question for today's lecture? Okay, now we are moving into the different reactions. After we learn this oxidation, next week we are moving to triple bond, alkyne. After that, alkyl halide. So that's very standard reaction in organic chemistry. In alkyl halide, and it's a reaction. Okay, we are moving to that. So more and more reaction will be accumulated from now on. Every time you learn new things, it's good to summarize right away and solve those problems in front of the class. Okay, other questions? Okay, midterm exam, I was worried that maybe everybody got the full score of 60.